Hey everyone, and welcome. Today, we're going to tackle a specific type of recurrence relation that you'll see pretty much everywhere in algorithm analysis. You know, the ones that count down one step at a time. By the end of this, not only will you get how to solve it, but you'll have a super powerful tool to solve similar problems in just a few seconds.
So here's the game plan. We'll kick things off with our target recurrence relation. Then, we're going to solve it two different ways. First with a really visual tree-based approach, and then with a more formal algebraic one. All of that is going to lead up to an amazing shortcut that makes this whole class of problems way easier. And then, of course, we'll wrap up with the key takeaways.
All right, first things first. Let's get a really clear look at the specific problem we're solving today. What is this recurrence relation actually telling us?
This is our central question. So imagine you have an algorithm. For a problem of size n, it does a little bit of logarithmic work. Think of it like a quick search. And then it calls itself on a slightly smaller problem, size n-1. The question is, how do we add up all that work to find the total cost?
Let's really break this down. T of n is the total time for a problem of size n. The formula tells us that to get that total time, you first have to figure out the time for a slightly smaller problem, t of n-1, and then you add on some extra work, which in this case costs log n. This whole process just keeps going until we finally hit our base case, t of 0, which we're saying just takes a constant amount of time, just 1.
Okay, on to our first method, the recursion tree. Honestly, this is a fantastic way to actually see what's happening under the hood as the function calls itself over and over again.
So right at the top of our tree, the root, we have our initial call, t of n. The work that's done just at this level is log n. And from there, this node creates just one child, the next recursive call, which is t of n-1.
Now we follow that branch down one level. The call to t of n-1 does its own bit of work, which costs log of n-1, and then it calls t of n-2. You can already see the pattern forming here, right? Each level of the tree is doing just a little bit less work than the one before it.
And this chain just keeps on going, from n-2 to n-3, and so on, all the way down the line until we finally hit our stopping point, the base case, t of 0. What we've really built here is a long, skinny tree that's basically just a single branch with n different levels. So, if we want to find the total time complexity, what do? It's simple. We just need to add up the work done at every single one of those levels. That gives us this big summation right here, the sum of logarithms, all the way from log of n down to log of 1. Now, how in the world do we simplify that? Well, this is where a really fundamental property of logarithms comes in to save the day. It basically says that adding a bunch of logs together is the exact same thing as taking the log of their product. This one property is the key that's going to unlock the whole solution. So by applying that property, our big long summation just collapses into a single, much nicer term, the logarithm of n factorial. Now that's an expression we can work with. And this leads us right to the finish line. While log of n factorial is the precise mathematical answer, in complexity analysis, we usually work with approximations. And it's a well-known fact that log of n factorial is very, very closely bounded by n log n. So we say its complexity is big O of n log n. And that's our answer from the tree method.
Okay, so we got an answer with the visual method. But let's be thorough and confirm it with a more rigorous algebraic approach, the substitution method. This will prove our visual intuition was on the right track.
We're going to start with our original equation. Now we know from the definition that t of n-1 is the same as t of n-2 plus log of n-1. So let's just take that and substitute it right back into our main formula.
After that first substitution, we get this new expression. You can already see the pattern starting to build up, right? We're just accumulating these log terms. Let's do it one more time. Let's substitute for t of n-2 just to be sure.
And there you have it. After another round, we've got t of n-3 plus this growing series of log terms. The most important part of this whole method is just recognizing this repetitive pattern.
Now, instead of doing this over and over, let's just generalize. After k rounds of substitution, our equation is going to look like this: t of n minus k plus a whole summation of these log terms.
So when does this all stop? Well, it stops when we hit the base case, which is when the argument inside t becomes 0. So n minus k must equal 0, which of course just means k has to equal n. If we plug k equals n back into our general formula, we get this final, fully expanded form.
And since we already defined t of 0 as 1, and we know that the sum of all those logs is just the log of the product, we end up with 1 plus log of n factorial. Hey, that looks familiar. It's the exact same result we got from the recursion tree, which, again, simplifies to a time complexity of O n log n. Two different methods, same exact answer. You gotta love when that happens.
All of that work, that was all to build up our intuition for the real big insight of this whole explainer. A shortcut that lets you solve these kinds of problems almost instantly. Let's check it out.
Just take a look at this table. When the extra work at each step was just a constant, 1, the complexity was O of n. When the work was n, the complexity was O of n squared. And for our problem today, with log n work, we got O of n log n. You see the pattern here, don't you?
And here it is, the shortcut. For any recurrence relation that has this form, t of n equals t of n minus some constant plus some function of n, the complexity is generally going to be O of n times f of n. Why? Well, it makes sense if you think about it. You're performing that f of n work roughly n times as the recursion counts all the way down from n to 0.
Okay, now a really important warning. This shortcut is powerful, but it's not a magic wand. It has very strict rules. It absolutely does not work if there's a number out front, a coefficient like 2 times t of n minus 1. That completely changes the recursion tree from a simple chain into a big branching tree. Also, that c value has to be a constant, so be really careful you don't misapply this rule.
All right, let's wrap this all up with a quick summary of what we learned and a final thought to chew on.
So to recap, we've now seen how to solve t of n equals t of n minus 1 plus log n, both visually with the recursion tree and algebraically with substitution. We found its complexity is O of n log n. And most importantly, we uncovered a super useful shortcut for this entire class of decreasing by a constant recurrence relations.
And that brings us to a final interesting question. Our shortcut is great for when we subtract from n, but a lot of really powerful algorithms, like binary search, work by dividing the problem. So what happens to a recurrence like t of n divided by 2? Well, that's a whole other story for another time. Thanks for watching.